Welcome, everybody, to the fourth installment, I believe, of Dr. Eigenstate Explains. This one's going to be another short one, quick one. The concept that we're talking about in this episode, this installment, I should say, it's another simple one. I could make it complex by going into the math. I don't know why I did that. That wasn't what I was trying to do. But my goal in this series isn't to dive super deep into some of the mathematical concepts. Naturally, some of them might appear, but my goal isn't. I'm not trying to teach math here. I might explain what math is saying as it relates to this, but the Dr. Eigenstate Explains series is not going to have a lot of math because I feel that, honestly, you lose a lot of people there. If you want to learn more about the math, there are many other channels that focus strictly on math. 3 Blue 1 Brown is a good one. The Number File is another good one. There's several out there. But moving on, clean off my screen on my iPad here just a little bit. Getting some extra streaks there. In this installment, we are going to be talking about uncertainty. Namely, if I could keep my screen clean. Heisenberg's certainty print. If I could spell correctly, that would really help. But I probably shouldn't talk when I'm trying to spell because I'm not very good at doing both at the same time. Heisenberg's uncertainty principle is going to be the main subject of this installment. I don't know whether I should explain the origin of it. I suppose I can. I don't have to get too mathy to explain it, but it involves something that is called I don't like the pressure sensitivity on this. There isn't a way to shut it off, so I don't know what to do. That's supposed to be an M. Fourier, that is pronounced Fourier because he's French, not Fourier. Fourier transform. And essentially what a Fourier transform is it's a fancy mathematical tool that allows one to decompose a function into constituent frequencies. And if we do something like that with, say, position or momentum, what we'll find is that as we localize in one domain of that function, say position, values for a complementary domain like momentum will become more spread out. And the domain of a function are all of the valid inputs for that function. So that is basically what a Fourier transform is. And so what we get from that is that the more we localize position, the more spread out momentum becomes. So to give an intuitive picture of this, red is going to be position and blue is going to be momentum. But first, we're going to make something that's going to be requisite here, standard deviations. Hopefully everybody knows what those are. They're not hard. They help us understand probabilities and things like that. So red is going to be our position, blue is going to be our momentum. You can have something that looks like that for position. You could have something that looks like that for position, or you could have something that looks like that representing your position. And you'll notice that I'm just going to make this easy, that with each one of these corresponding functions, I guess you could say waves, you're getting more localized, so that this last one here is really localized within this standard deviation here. And as I said last time, in the last installment, what that does for us is it allows us to confidently assign a value to the observable that we're measuring. So in this case, it's position. If your position is within this standard deviation, then there's a very, very, very high likelihood you can confidently say that this is the quantity that you're measuring for position. Whereas, if it's, I don't know, I'm supposed to be in red, if it's more spread out over standard deviations, it's most likely to be found in this one, but there's a good probability it could be found here. There's also a decent probability it could be found in here. So what we're doing here is we are localizing the wave. That's what I'm going to use here. I think it's a good word to use. We're localizing the wave into a standard deviation so that we can make confident statements about what quantities to assign to that observable. And the thing is, with uncertainty, and before I dive into that, just to recap, I mentioned complementarity in the last installment. Complementarity is the idea that you can have two different observables, and they are complementary to one another. And what this means is that the more precisely you know one, the less precisely you know the other, and vice versa. What that's really saying is that with one, say, position, and then blue is momentum, the more you reduce position to within a standard deviation, so it gets more precise, the less precise momentum gets, or the more standard deviations over which momentum can be defined. And vice versa. If you were to get more precise with momentum, the less precise you would get with position. And this can be represented with a handy equation that I'm sure some of you may have seen. I gotta make sure I write this symbol correctly. I think I'll have it right here. Let's do this. That doesn't look, I don't like the way that looks. Oh, I know what I did. There we go. Sigma. That is a really poor looking sigma, but that's what it's supposed to be. So you would say sigma, which represents the uncertainty in, or more appropriately, the standard deviations over which this, say, quantity or observable is defined, by, so it would be times, we're not going to write the time symbol, sigma p must be greater than or equal to h bar, which is the reduced Planck's constant. I'm not going to get into what that is. It's not relevant to this video. Over 2, or 1/2 of the reduced Planck's constant, which is just h bar over 2 is just a quantity. And what it's saying is that the standard deviations in position multiplied by the standard deviations in momentum must be greater than or equal to the quantity defined by this, which simplistically says we can't know either position or momentum precisely simultaneously. And that comes back to the standard deviations thing. The more standard deviation, or rather the less standard deviations over which some quantity is defined. So to recap, the less standard deviations over which some quantity is defined, the more standard deviations over which its complementary observable will be defined. So the more precisely we learn, or the more we hone in on the position of some quantum object, we will start destroying knowledge about its momentum, and vice versa. The more we hone in on what the momentum of the quantum object is, the less we will know about its position. And a lot of this can be reduced. I really wish they would let me have a bigger eraser. Can be reduced to how those waves, or wave functions, waveforms, are structured in a coordinate space. Momentum is going to be generally, and I'm going to do this poorly, but just bear with me, it's going to generally be continuous, just a sine wave. Whereas position will still be a wave, but there is going to be a part where the amplitude is a little higher. And so the higher you get an amplitude in a position, the less equal that wave is, which means that you're learning about where the object is, but you're not learning really anything about its momentum. And the less you localize any one of the amplitudes of the wave, the more you're learning about its momentum, but the less you're learning about where it's at. And this is essentially what uncertainty tells us. It tells us that with two complementary observables, if you increase your precision in your knowledge of one, you are decreasing your precision in your knowledge of the other, simply because of the way that the wave function defining these quantities is structured, put simplistically. So some of you might be asking, well, wouldn't there be a way to sort of even it out, where you could say, yeah, we know the position a little bit, we know the momentum a little bit, we don't know either perfectly, but it's enough to define the system. And that's a question I've asked myself, and the answer is no, we can't do that, because in such an instance, both of the values would be so imprecise that you wouldn't really be learning anything about the system or what it's doing. You would have to start increasing your precision rather, of one of those particular observables in order to really know anything about the system. And then uncertainty takes hold, and the more precise you get with that observable, the less precise the complementary observable is going to get. And again, that just goes back to the way that the waveforms are structured and the way that we can mathematically describe them. We're not allowed to define both of these properties precisely simultaneously. It just doesn't work. So that is what uncertainty is. It is a foundational concept in quantum mechanics, so I figured I should probably do a video on it before moving on from quantum mechanics, since I've done 4 videos on it. The next video I'm going to be touching on some other concepts, probably in cosmology, and the next video is probably going to be a little bit of a longer one. It could run close to, if not over, an hour, so stay tuned for that one. That one will release again next Thursday at 7 p.m. Central Standard Time, 8 p.m. Eastern. So I hope you enjoyed this video. I hope you learned a little bit more about what uncertainty really is, what it's really telling us, and why it exists in the first place. And with that, I leave you with per causam nos perfectum, or through reason we progress.